with the concepts of functions and subroutines. Okay, so you see, um, yesterday we had seen that you've got the instructions and data sitting in memory like this: operation, data, data, operation, data, data, like that, depending upon what kind of one word or two word or three word operations or four word or five word operations, whatever it is. The first word is always an operation, and if it requires any data, then the data comes subsequently afterwards, and it all is brought into the computer with the timing cycles. And the first timing cycle brings in the instruction code, which is a number, and the next two are data, or the next one is data, and so on and so forth. So it's by these timing cycles that the computer decides which one is which and acts accordingly. Okay, now in C you have done, you see, let's just have a quick look at a function. Okay, Shunita Vishwas is joining us now. So in C you've done a function like this. So this is a f, let's say that int x int y. Okay, x equals to 5, y equals to 6, x equals to x plus y, and then so printf %d x. Okay, and you have a function like this, and what you do is, let's say in the main function, let's just draw it separately. The main function, in all the code, somewhere you call f like this. Okay, and it ends here. Now, as you know that from your experience in C programming or any other programming that you've done, you know that the concept is that these lines are executed, well, whatever they are. There may be function calls, there may be some assignment, there may be some printing statements, whatever they are, scanning statements, whatever they are, they're there. This is followed by a call to this function f, and after the f function finishes executing, you come back to this point. So how is this achieved in the hardware level? So let's just look at a very simple example to understand it. As usual, so this is all, this is a memory address, okay, and these are all lines. Now the thing is, let us say that the if function, okay, has been written from here. So we've got, so this is say x, this is x plus 1, these are all memory locations, x, x plus 1, x plus 2, etc., etc. It's all memory locations. Okay, and let us say that this is the main function sitting in here. The binary version of the main function starts from a location, say y. This is y plus 1, y plus 2, etc., etc., etc. Like that it goes on. Now in the computer here, which addresses this in a simplex mode and carries data to and from this main memory in a duplex mode. So this is data, this is address, and obviously it looks like this. It's got a control unit that controls all the operations according to the timing cycle, and apart from these, it has got several input and output lines for control signals coming in and out of it. Control signals, many control signals can be there. The core of the computer which works is the ALU. That's called the core of the computer. That's where the main activity goes on. That's where the arithmetic and logic circuits are. So all the basic operations like adding, subtracting, multiplying, and transfers and shifting and all of that, and if it is greater than, if it is lesser than, if it is equal to, whatever it is, okay, that goes on in there. Then there are the memory registers here. Several memory registers are there. One of those belong to the ALU. It is called the A accumulator register, but it is actually a register nonetheless. Then there are other registers. Like for example, in an 8085, there's a B register and a C register, D register, and an E register, and there's a W and a Z register. Okay, and there are several other special registers. For example, so these are for specifically for data and data. Well, data. No, it's all data. So we'll just call it data. There are special data registers that hold instructions called the instruction register. Then there is a address register for the next data to come in. It's called the program counter. And then there are other things like the stack pointer and the status register SR, which is the which shows whether there is a whether the sign is positive or negative, or whether there is a zero result or a carry, and so on. Uh, then the stack pointer register is there. Now, this is something of very much now there are other registers as well, which in any computer version. Now we are just talking about box standard 8085 processor, which is a very old processor. We don't use it anymore. We just use it for academic purposes because it's very simple to learn. But all the other processors which have come after that are very complex processors, okay, and they may have several more registers. Well, they are there for a purpose, either for holding data or for holding the instructions or for the program counter or for the status register. Obviously is there. Now in 8085, the number of statuses is mostly that we use are S, Z, and C. I keep on saying Z because it's an American term. So the term for Z in American is Z. So that is why I'm saying Z. You can call it Z as well. So the S, Z, and C indications are there. Now, particularly what I'm going to be focusing on is the stack pointer. So stack pointer. To know why we use a stack pointer, we must understand how a function actually works. So we'll start off with the programming language itself, C, because this is something C or C++ is the same thing. It's basically the same way it does it. Every programming language does, because you've learned it, so it will be easy for you to uh, to corroborate. So let us say that this is the hang on, I'm just going out of focus. Just one second. So let us say this is the main function. This is the start of the main function. This is the main going on, and let us say this is the f function somewhere in memory. So the thread of execution looks like this. At some point of time here, there is a call to an f, well, and one call to an f, to the f function. So basically the control then moves to f. We call it function call, we call it a jump, whatever you call it. It means that the control moves from this part of memory to the other. Now when that happens, next is when you finish executing f, this now comes back to the position right after the call. So if this was statement number X, after f is finished, okay, we start off with statement number X plus 1. So that means automatically the control comes back. The control comes back to position X plus 1, and we continue like this. Now if there is another call to f, I mean, for example, this f might be the printf function, for example. So if it is the printf function, for example, we call printf many times, we call scanf many times. So once again, if there is a call to the f function, once again the control will jump to the start of this, and after finishing it will come back to the next line and continue onwards. This goes on until main is ended, from where we exit. Now where do we exit? Normally we basically give the control back to the OS, operating system, which is managing all the processes and the memory and everything else. But look at this thread of execution. We call it a thread of execution because it's a fancy term. When we look at a program, all the statements are there. We connect all the statements one after the other. The line is called the thread of execution. So this is a single threaded program, which means that it has got one single line of execution, goes from top to end without any branching. Whenever there is a branching, we say we've reached that there are, say, if there are two branches, three branches, we say there are two threads of execution, and so on and so forth. Except that, just remember, we have to take the branches not as normally when we mean by multi-threaded programs, we don't see that as any one of the branches being taken and the others being forgotten, but we mean that all the branches of execution will be happening at the same time. I'll give you an example. So follow very clearly. This is, let us say, you can travel three different paths, and then we join here, and we carry on till we exit. Let me explain what happened here. We came to this point here. Let us say this point is P, and from there we either travel a path P1 or travel a path P2, which is a straight path, or travel a path, so this is an or travel a path P3. This happens, for example, if we have a if else statement, if something, else if something, and else. Here we have achieved this. We either follow this, or we follow the next path, which is the else if, or we follow the else part. Now, as you can see, there are three paths of execution. But can this be called a multi-threaded program? We don't really call this multi-threaded, because you know why? Either our path will be this, or our path will be this, or our path will be this. We do not execute the three paths at once. You can imagine that. So if the if is valid, the other two are invalid. If the if is invalid, we go to the else if, and if this is valid, the other becomes invalid. If was already invalid. If the if is invalid and the else if is invalid, then the else part is executed. So we see that when these are mutually exclusive. So that means that if the path A is taken, let's call this path A, or sorry, we have already got a name for it, P1, P2, and P3. If P1 is taken, then that's the path. P2 is taken, then that's the path. P3 is taken, then that's the path. We cannot take the three at once. So we cannot really call it a multi-threaded. We don't really call it a multi-threaded program. Why? Because we have only got one thread of execution, whatever it is. The thread may be this or this or this. So in this case, we don't normally call it a multi-threaded program. However, look at this program. Now, here, once again, we have a, let's say we call it P4, just to avoid confusion in the, in the video later on. This is P5 and this is P6, and this point of segregation, once again I'm calling it P. So the way it works is we go up to P, then we travel up to, and let's call this point of convergence as P dash. Let's say we travel the path P4 to P dash, and we also travel the path P uh, say 5, and we also travel the path P6, and then we meet at P dash, okay, where the execution could be P, P4, P5, P6, P dash, or it could be P, P5, P4, P6, P dash, or some order thereof, where we travel all the paths. So these are inclusive in nature. That is, every path includes every other path. In this case, all the different paths are executed. Now the thing is that what we have done is, with a special arrangement, it is generally provided by the programming language itself. For example, Java has threading, or Java supports threading. By special arrangement, we have created small threads of execution that act as small programs, and we tackle each of the threads one after the other. And then we converge at P dash, and then we carry forward. Why we do that? Let us see. In a specifically in an environment where, let us look at memory management for the time being. In an environment where we have a single processor machine, okay, there are several programs which are sitting in main memory. Okay, this is a program 1, this is a program 2, this is a program 3, and this is a program 4. Now, how does the processor, which is just one processor, how does it actually cycle between these two? The answer is by time sharing. It's a very basic concept, which I'm sure that you all have learned from uh, what's it called, your operating system and others. It's a very important concept of computer architecture. How do we time share? According to some clock pulse, let us say we give this 100 microseconds. Let us say we give these 100 microseconds. Let us say we give these 100 microseconds. And then we give these 100 microseconds, something like that. Or we, for example, we may give it one job. Then if we can divide it into several jobs, then this is one job. So for one job each, one job, then it can be this, or it can be machine cycles, whatever cycles it is. I'm saying that we divide it into all these time frames, and we give one time frame to P1, and after that is satisfied, we go to the second one, then the third one, then the fourth one, and the P1 waits. Then we come to P2, then we come to P3, P4, again P1, again P2, and while one is being serviced, the other waits. So it looks like this. Let us say that we have all got the same priority. That means they're all of equal importance. So in that case, we will serve them as a first come, first serve basis, first come, first served basis, in a round robin way. Round robin way. Otherwise, what will happen is, if you only if there is no round robin, what will happen? Only P1 will be served, P2 and P3 and P4 will sit idle, so on and so forth. So we don't want that. So, for example, if P1 is IOing, that means if it is inputting or outputting, it doesn't require the processor, because the input controller, as you've done before, will be handling this. So the processor will then sit idle. So why sit idle? Just serve P2, then you serve it for one job, and then go to P3 like this. So in this case, although it looks to us that every computer in every computer that we use, it looks to us, because it's so fast, it looks to us as if all the jobs are running at the same time. The jobs are not running the same at the same time. They're being time shared. The jobs can only run at the same time if we have multiple processors. Then P1 can be processed by, so if I can draw this with a blue, so P1 can be serviced by processor 1. Let's call this proc 1. P2 can be serviced by proc 2. P3 can be serviced by proc 3. P4 can be serviced by proc 4. In that case, we have got truly that the processes are running simultaneously. Otherwise, it is not so. There is another concept called multi-core, in which case the same processor has got the CU and then a set of, and then we have got divided it into several ALUs, ALU1, ALU2, ALU3, like this, but they've got the same data interface. So data comes in and gets redistributed to the several ALUs. Your multi-core processors are just like that. So it's got one processor with several cores. My phone, that one that I'm using at the moment, is it is an octa-core processor that is in there. So it has got 8 ALUs in there. Although the data interface is the same. So the data comes in and gets going into the various ALUs. Once the ALUs finish their work, then the data goes out through the same processing. So there is always this small bottleneck, which is called the von Neumann bottleneck, that there is only one data interface. It may face that. But truly, it will be run parallelly. But when the job is being done in several ALUs, we can say that it is being done parallelly. But if you want to achieve true parallelism in executing the jobs, you'll have to have multiple processors which run in parallel with each other. And even then, you have to have one processor which will act as a master that will provide the other processors with the jobs. Okay. And then also, when it is providing, let's say processor 1 is there, which is providing the other processors with jobs. It'll provide 2 with jobs first, then 3, then 4, like that. The same job cannot be sent to all the processors. You are very sure of that the same job cannot be sent to all the processors. In that case, obviously it will first send one job to processor 2, then the second one to processor 3, third one to processor 4. So again, there is here some seriality. Now let us come back to this single processor scenario, which is the general case, as we will take it as the general case. That is time sharing. Now, if on the other hand, cut to multi-threading, if on the other hand, we can multi-thread the process. Let's say we multi-thread the P2 process. So what is a process? Process basically, as we all know, is a program in execution. That means that the runnable binary file that is sitting in main memory that is being used at the moment for execution is the process, and it has come from a corresponding programming file. Now, let us say process 1, now there is this single processor machine is there. So the ALU is there, the registers are there, and there is this memory in which there is process 1, there is process 2, process 3, and process 4 as before, except, so that's P1, P2, P3, P4, except that P2 is now divided into, say, 3 sub-processes like this. We call them threads. So T1 dot P2, T2 dot P2, and T3 dot P2. So these are threads of execution. First thread of P2, second and third. This acts as small processes, lightweight processes. Now what will happen? P1 will be served first. Now once again I am assuming that they are same priority, served on a first come first served round robin basis. So P1 is served first. Then what happens? What used to happen was we used to have P2, then P3, then P4. So previously the path would look like this: P1, P2, P3, P4. But now it looks like this: P1, rather, I beg your pardon, I beg your pardon, P1, it will be in red, P1, then T1 dot P2, T2 dot P2, T3 dot P2, and then again P3 and then P4. What is the difference? The difference is for 3 cycles P2 is being served. For 3 jobs or 3 cycles or whatever, etc. So for 3 units of time, that is there, which would normally, this would be P3's chance, this would be P4's chance. But because of this monthly threading nature of it, for 3 times P2 is being served. And if you divide the tasks that you're doing in P2 into 3 different tasks at this moment and give one to T1, one to T2, and one to T3, then P2 and then P2's 3 tasks or 3 threads rather, with the 3 tasks, will be serviced one after the other before it goes to P3 and P4, and so this will finish in a lesser amount of time than if it was not multi-threaded. Besides that, there are several other reasons that we thread. Okay, Divya is asking why not T1 dot why not? Sorry, Divya, can you just say it? Because in our example, P1 and P3 and P4 are not threaded. Only P2 is threaded. Hmm. I mean, if you do not thread it by special command from your programming language, it is a programming language feature. It'll actually be P1, P2, P3, P4. But because we have used threading in P2, we have got these 3 threads. Now, apart from being fast, they are different sort of advantages to this. One other being that 3 different tasks can be handled, which we normally, if it is P2, then this will be dedicated some memory. This will be dedicated some processor time. Processor time we just dealt with, but then it would be dedicated some memory, some I/O time, etc. But if you got 3 threads, then P2 can handle all these different IOs and memory issues that it can do. It can handle all these with much more ease. An example of this is a multi-threaded server, internet server. And what happens is a server is a program, obviously, not just the hardware, but it's also the program that is also a part of the server. Now, the program, that server, if it was single-threaded, let us say that you have got some resource somewhere in the net. Some repository is there and you are reading something from the net. Now, the server is handling your request. Now what will happen? Let us just draw a bit of a barrier here and let's just see. If you've got a server which is a single threaded, so one thread, then this is the thread, your request comes in and the response goes out, okay, according to your authorization. Now, say that we have one user, 2 users, and 3 users. So when one is being serviced, the others are waiting. When the other is being served, then the others are waiting, like that. However, that is exactly why we make the server, say, multi-threaded. What will happen? This server will contain 3 different threads, same server process, but having 3 different threads, so that one user may be served by one thread, another user may be served by another thread, another user may be served by another thread, as simultaneously as possible. As simultaneously as possible. So the access to the web resource, let us say you're wanting to read something, for example, Google servers. So you are or let's say Wikipedia, for example, if you are reading the same article as everyone else, then that is being served by a multi-threaded server, because it is having to give you all the data while it is giving the others the same data also. How is it doing that? One way, or one basic thing about it, apart from other things that are there, that are network issues are there, but other